Good day, I am Puan Chow from SMK Common Typing. Let us learn the third subtopic in Chapter 7, Quantum Physics. Einstein Photoelectric Theory. In this subtopic, we will learn about Einstein photoelectric theory, work function and threshold frequency for photoelectric effect, generating photoelectric current in a photocell circuit, and photoelectric effect applications. Einstein's photoelectric theory. In subtopic 7.2, we learn about photoelectric effect. Albert Einstein introduced a photoelectric theory that successfully explained all the characteristics of photoelectric effect in related experiments. He was awarded the Nobel Prize in 1921 for this achievement. This theory is named Einstein's photoelectric theory. Einstein applied Max Planck's idea of energy quantum. He suggested that energy is carried by light particles called photons. The energy of each photon is directly proportional to the frequency of light. The formula to relate them is E equals to hf, where h is Planck's constant. Each quantum of light is a discrete packet of energy. There are many energy packets in a beam of light that shines on the metal surface. When a photon arrives at a metal surface, the photon energy will be fully absorbed by an electron in the metal. The photon energy is used to release the electrons from the metal, while the extra energy will become the kinetic energy of the photoelectron. The electrons on the metal surface will acquire maximum kinetic energy compared to the electrons inside the metal. For the electrons on the metal surface, after absorbing the photon energy, it only required minimum energy to release a photoelectron. Thus, for the electrons on the metal surface, it acquired maximum kinetic energy. The formula to relate them is E equals to W plus Kmax. E is photon energy, W is work function, Kmax is maximum kinetic energy. We learned before this, E equals to hf. We also know that kinetic energy equals to 1 over 2 mv squared. Now, this kinetic energy is maximum, thus the velocity also maximum. Now we can rewrite. We can write as hf equals to W plus 1 over 2 mv max squared. Einstein's photoelectric equation is in accordance with the principle of conservation of energy. What is principle of conservation of energy? Principle of conservation of energy states that energy cannot be created. Energy cannot be destroyed. It can only be converted from one form to another form. In 7.2, we learn about threshold frequency. That is the minimum frequency required to produce photoelectric effect on a metal. That is also the minimum frequency to emit electron from the metal surface. Now, at the threshold frequency, photon electrons are emitted without any kinetic energy. So 1 over 2 mv maximum square is 0. We can rewrite the formula that we had learned. hf equals to W plus 1 over 2 mv maximum square. So this 1 over 2 mv maximum square is 0. Thus, hf equals to W plus 0. F is threshold frequency, so we put a 0 here. So W equals to hf 0. We continue to learn about work function and threshold frequency for photoelectric effect. Here comes the definition for work function W. Work function is the minimum energy required for a photoelectron to be emitted from a metal surface. We learn about threshold frequency. That is a minimum frequency for a light photon to produce photoelectric effect. The graph below shows the relationship between the maximum kinetic energy of photoelectrons and the light frequency. There is one intercept at the frequency axis, that is, the threshold frequency. At the threshold frequency, photoelectrons are emitted without any kinetic energy. So that is why kinetic energy here is 0 for threshold frequency. At the threshold frequency, photoelectrons are emitted without any kinetic energy. Thus, the relationship between work function and threshold frequency of a metal can be determined by W equals to HF0. Unit for W, work function, is joule or electron volt. 1 electron volt equals to 1.60 times 10 to the power of negative 19 joule. The photoelectrons will acquire kinetic energy when light frequency exceeds the threshold frequency. The higher the threshold frequency of a metal, the higher the work function. This means that the minimum energy required for photoelectric effect to occur is also higher. Different metals have different threshold frequency, as shown in the graph below. For this graph, all the graphs are with the same gradient. Let's carry on to learn about generating photoelectric current in a photocell circuit. This figure over here shows a photocell circuit consisting of a glass vacuum tube. Let's take a look at the structure. This is the cathode. It is a semi-cylindrical cathode which is coated with a light-sensitive metal, and it is connected to the negative potential. Over here, we have anode. This anode is a metal rod. It is fixed at the axis of the semi-cylindrical cathode, and it is connected to the positive potential. When this photocell is illuminated by light, the production of photoelectric current is produced in the circuit. These are the two examples of common photocell, cesium and lithium. From the values, we can see that the higher the work function, the shorter the maximum wavelength required to produce photoelectric current. As the light intensity increases, the photoelectric current in the photocell circuit also increases. Let's take a look at some examples of applications of photoelectric effect. LED lamps along the road, which are powered by solar cells, are energy efficient and environmentally friendly. In daylight, the photoelectric effect on solar cells enable the electrical energy to be stored in the battery. The charge controller here will manage and protect the battery from overcharge. At night, the LED light lamps will light up with the power from the battery. The Noor Complex Solar Power Plant, located in the Sahara Desert, is the world's largest concentrated solar power plant. There are 4 types of concentrated solar power technologies. The picture here shows us one of them, which is central receiver. Central receiver, as you can see, there is a solar tower here, the receiver is here, and this solar tower is surrounded by heliostats. Heliostats are devices that consist of mirrors, usually plane mirrors. These heliostats can be individually controlled and moved in order to face the sun, and it will keep on reflecting sunlight directed towards the central receiver. Previously, we learned about photocells, As light intensity of the photocell increases, the photoelectric current in the photocell circuit also increases. In this application, it shows us that photocell is used as a light detector at the automatic doors. Take a look at this diagram. The emitter emits infrared to the receiver. The photocell is the receiver. When there is an object block the emission of infrared, photocell cannot detect light. So when photocell cannot detect light, what happened to the light intensity? The light intensity decreases. So the photoelectric current in the photocell circuit also decreases. Thus, the door will remain open. The image sensor is a main component in high-resolution cameras. CMOS sensor is used to convert light into electrical signals, which can be processed to form digital images. The operation of the ISS, International Space Station, depends on the source of electrical energy generated from solar panels. Gimbals are used to rotate the solar panels so that the solar panels can face the sun and track the sun to provide maximum power to the space station. That is all for subtopic 7.3, Einstein's photoelectric theory. Thank you.